Hello, this is Dr. Joe Trout from the physics program at Stockton University. And this lecture is on chapter 2, and it talks about the composition of ice cream. If we look at ice cream labels, you'll see a list of ingredients. And for instance, this ice cream contains milk, skim milk, cream, sugar, corn syrup, and contains less than 1% of natural flavors, caro bean gum, gar gum, carrageenan, mono and disaccharides, cellulose gel, cellulose gum, and some coloring. Here's another brand of ice cream. And if you look at the list of ingredients, you see milk, cream, corn syrup, sugar, whey, non-fat milk, cellulose gel, and many of the same ingredients as the last ice cream. But what are these things, and why are they used in ice cream? And what's the purpose of each one of these ingredients? So let's look at the ice cream characteristics. And first, it's frozen when eaten, and it melts to cool and refresh, and it tastes sweet. The aroma is actually suppressed until it's eaten. So you may know that much of your taste comes from how things smell, right? And from the odors that come off or the aromas that come off of the food. But the aroma is suppressed until it's eaten. So it's also creamy and smooth, and appearance is important. And always there's a choice of flavors. So if we look at the ice cream industry, it's in competition and has a synergy with many things. So for instance, baked goods and beverages and confectionery chocolates and dairy, all of these other industries both compete with the ice cream industry, and have a synergy with the ice cream industry. So, for example, we use chocolate to coat ice cream sometimes and come up with things like Eskimo pies. So, first, let's look at the nomenclature of ice cream. So, we have ice cream, we have frozen custard, which is French style. We have reduced fat ice cream, low fat ice cream, light ice cream, non fat ice cream, and frozen yogurt. And by the way, we'll explain each one of these as we go along. Then there's sherbet, water ice, Italian ice, and sorbet, Melorine, frozen dairy desserts, frozen confections, milkshakes, and shakes. So the characteristics of all of these frozen desserts is that they're actually partially frozen. So if they were completely frozen, it'd be like eating an ice cube, right? And it wouldn't be very enjoyable. They're also cooling and refreshing. They have a sweet taste for the most part. And the backbone of every product is a syrup of sugar and water. And the syrup is manipulated to obtain the desired taste and texture, consistency and appearance of these frozen desserts. So how is it frozen? Well, it can be done a couple of different ways. So one is while being stirred or agitated. So ice cream is always done in this method. So we stir it while it's freezing and to incorporate air into the ice cream and produce something called overrun. It could also be frozen quiescently, which means without stirring or agitation. So for example, if you had what we refer to as an ice cream popsicle, right, which has ice cream coated in chocolate, for example, what's inside is not actually ice cream because it's not stirred while it's being frozen. And you might notice that there's a slightly different texture to it. So all of these frozen desserts, they're either stirred while they're being frozen to incorporate air, such as ice cream, or quiescently, or a combination of the two. So it might be stirred for a little while and then um, frozen the rest of the way without agitation or stirring. There's also a degree of freezing that takes place. So, for instance, we have hard frozen, or we might want it frozen enough for it to be easily scooped, such as in if you go to a ice cream shop that serves mostly ice cream cones, and there's soft serve ice cream where it's not hardened at the end. And finally, of course, we have things like milkshakes that are even less frozen than soft serve ice cream. Just to remind you, the legal definition of ice cream, it's ice cream is a food produced by freezing while stirring a pasteurized mix containing one or more optional specific ingredients specified in the next section. Right? And ice cream must contain a minimum of 1.6 pounds of total solids and must weigh at least 4.5 pounds per gallon. This is prior to any additives that you add. So, for instance, strawberry ice cream. This is before you add the strawberries. So, a lot of different ingredients go into ice cream. So, for instance, there's milk fat. And this is fat present in milk or butter or cream or butter oil. There's also milk solids not fat. They're also known as MSNF or SNF or serum solids. So dealing with solids that has no water. So it's whatever remains after you take out the fat and the water from milk. These include lactose, protein, and mineral, or we call it ash. So lactose is a sugar that's found in milk, and we'll talk more about protein in a minute. But normally when you think of protein, you think of eggs and meat. And minerals or ash, it's what's left over after you burn everything else away. Okay, so this is, and it's in essence the minerals that are left. So some common sources of milk solids not fat are skim milk powder, or non-fat dry milk, or condensed milk. Overrun is an expression of the mix volume increase due to the incorporation of air as vacuoles. So we whip up the ice cream and we add air to the mix. So 2 liters of ice cream from 1 liter of mix means the volume will increase by 100%. So if you remember in the lab where we made a simple vanilla ice cream, we took milk and cream and sugar and a little bit of salt and vanilla, and we mixed it together. So this was the ice cream mix. Then, while we were freezing it, we churned it and kept air, forcing air into it. And the volume increased. So if it's 100% overrun, then we get 2 liters of ice cream from 1 liter of the mix. When 1 liter of mix yields 1.8 liters of ice cream, then the volume increases by 80% and the overrun is 80%. So if we look at overrun, it's the volume of the product minus the volume of the mix divided by the volume of a mix times 100%. So for example, if we get 1.3 gallons of ice cream from 1 gallon of mix, that's 1.3 gallons minus 1 gallon is zero point 0.3 gallons divided by 1 times 100. It's 30% overrun. Let's look at the backbone of ice cream. This is a syrup that contains 20% sugar and 80% water. So these are approximate values. So of that sugar, we have 15% sugar and 5% lactose or milk sugar. Right? So lactose is another name for the sugar that's found only in milk. So this backbone of this ice cream is just water and sugar at about a 20% sugar and about 80% water. So this is what happens when we manufacture ice cream. We adopt the formula in a recipe. We select, receive, and store ingredients. We assemble and process the mix. We add soluble flavor and color ingredients. We freeze and aerate in a swept surface cylinder. So like we showed in that home version of the ice cream maker, what happens is the ball spins around and the ball is really cold. So ice forms on the inside of the ball, and then you scrape off that ice as it turns around. Then we incorporate flavor pieces and variegates, such as nuts and strawberries and little pieces of candy. Then, if we're going to make a popsicle, we extrude it to shape when applicable. And then we package the product, and then we freeze quiescently to harden. So now, if you remember, we had soft serve ice cream after we took it out of the ice cream maker. Then we put it in the freezer to harden it. And then we store the product at a low temperature. So if we're going to make ice cream, first we blend the ingredients, then we pasteurize the mix, then homogenize the mix. So pasteurizing means that we heat it to remove bad bacteria. And then we homogenize it. That means that we mix it really well so that it has that everything's evenly dispersed and it's homogenized. Then we cool it and age it. We might add flavors and colors. Then we freeze it and harden it and store it. So characterizing materials in ice cream. So there's dairy ingredients, there's sweeteners, there's body and texture modifiers, and there's flavors and colors. So for example, there's milk fat. So this is the natural fat of milk from which butter is made. And it's consisting largely of glycerides of oleic and stearic and palmitic acids. And it's also called butterfat because butter is made out of it. There's also milk solids, not fat, and or it has various other names, the serum solids or milk solids, not fat, which are MSNF, and it contains the lactose, caseins, whey products, and minerals of the products from which they were derived. And they're an important ingredient for the following beneficial reasons, right? They improve the texture of the ice cream. And they also and how they do this is that it's due to the protein functionality. So these milk solids, not fats, give the ice cream a nice texture. There's also lactose. This is a disaccharide sugar composed of galactose and glucose, and it's found in milk. The whey is the serum or the watery part of the milk that is separated from coagulable parts or curd, especially in the process of making cheeses. And it's rich in lactose, minerals, vitamins, and contains traces of fat. We also want to make the ice cream sweet. So lactose, the milk sugar, is a sugar that's in milk, and it helps to make it sweet. But also we have sucrose, and this is a sweet, crystalline, dextrosatory, non-reducing disaccharide sugar, and it contains 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms. And it occurs naturally in most plants. And normally, this is our table sugar, if you will, and it's obtained commercially from sugar cane or sugar beets. And we'll actually watch a movie of how we get the sucrose from the sugar cane and sugar beets. We also have corn syrup solids. So corn syrup solids are made from concentrating corn syrup, and it's a liquid sweetener made from corn, and we just keep on boiling it until there's only about 10% water. So we take corn, you crush the corn, you keep heating it and let the water boil off, and what's left is this uh, thick sweet syrup. So corn syrup is partially hydrolyzed liquid cornstarch, and that is made with the addition of enzymes alumase and glucosamase, and which break down into glucose. So corn syrup solids is another type of sugar. There's also stabilizers in ice cream, and stabilizers are substances which make it possible to maintain the physiochemical state of foodstuff. So when you think of ice cream, you think of this, um, for instance, vanilla ice cream. It would be white and it would have a nice texture and it feels good in your mouth. And stabilizers help keep it that way. So, for instance, if you notice that if you kept ice cream in the freezer for a really long time, it starts to crystallize and it doesn't taste so good anymore, right? It doesn't feel right. And it's not harmful to you, it's just lost its appeal, right? Its physiochemical state. So, stabilizers help maintain this. Food stabilizers are often confused with preservatives, right? But there's a big difference between the two. Stabilizers are used to just retain the physical characteristics of the food, such as, right, so this creaminess and the firmness and things like that. Whereas preservatives prevent the spoilage of food. So food stabilizers increases the stability and thickness of the food by binding with large molecules. There's also something called emulsifiers. So this is an agent that forms or preserves an emulsion, right? Especially in any food additive. And these are such things as lecithin, and they prevent separation of sauces and other foods. There's also mineral ash, and ash refers to any inorganic materials such as minerals that are present in food. It's called ash because it's the residue that remains after heating removes water and all the organic materials such as fat and protein. Protein is a nutrient found in foods, right? So normally when we think of protein, we think of meat and milk and eggs and beans, and it's made up of many amino acids that are joined together. And it's a necessary part of our diet, and it's essential for the normal cell structure and functions. So when you think of protein, it's any of a class of nitrogenous organic compounds and it consists of large molecules composed of one or more long chains of amino acids. And they're essentially part of all living organisms, and especially as structural components of body tissue such as muscle, hair, and um, and as enzymes and antibodies. Carbohydrates are any of the large groups of organic compounds occurring in food and living tissues, including sugar, starch, and cellulose. So, mostly in ice cream, when we think of carbohydrates, we're thinking of the sugar. So, it's the sugar we add, and that can be in the form of the white table sugar that you put on your table, or it could be um, honey or corn syrup or anything that adds sweetness, and also the lactose, which is the sugar from the milk. Carbohydrates contain hydrogen and oxygen in the same ratio as water. So there's two hydrogen to every oxygen. And typically they can be broken down to release energy in animals and humans. So, for instance, if you're on a sports team and you need a quick energy boost, maybe you'll eat a chocolate bar, right? So your body can quickly break it down into energy. All right, so if we look at the composition of fruits, and desserts, we have things like non fat, low fat, reduced fat, regular ice cream, premium ice cream, and super premium ice cream. Well, you notice for non fat, there should be less than 0.5% of the ice cream should be fat. Okay, so for low fat, you have 3%. And for super premium, you have 18%. So what does that tell you, right? That tells you, and if you look at regular ice cream, there's 10%, premium, there's 12%, and super premium, there's 18%. So if you look at really high premium ice cream, it probably has a lot of milk fat. And let's face it, the milk fat tastes good, right? And it makes it for a good ice cream. If we look at milk solids, not fat, in order to get a good consistency, the less fat we put in, the more milk solids, not fat, we put in. So, for instance, in non fat, we have 0.5% fat. So we have 13% milk solids, not fat. If we go up to the premium end, we have 18% fat and only 8.5% milk solids, not fat. If we look at the whey solids, they're usually not in the low fat or reduced fat or non-fat ice cream, and they can add like a cheesy taste to the ice cream. So they're usually not in super premium either. But in regular and premium, there can be like 2%, right? So not enough to change the taste of the milk, of the ice cream, but there'll be a little bit. If we look at sucrose, sucrose is sugar. And if we look at corn syrup solids, that's also a sweetener. Okay. If we look at non-fat, there could be 10% sugar and 10% corn syrup solids. Now, I've talked to many food scientists and chemists, and they don't think that people can really tell the difference between the sucrose and the corn syrup starch, or the corn syrup solids, excuse me. And However, they kind of have a bad rap, the corn syrup solids. So you notice that super premium, they don't put any in because it looks bad on the label, right? But there's usually a mix. And for instance, in premium ice cream, there might be 11% sugar and 6% corn syrup solids. We also have stabilizers and emulsifiers. And you notice that the less fat there is, the more stabilizers and emulsifiers we have. Okay. So for super premium ice cream, there's like 0.2%, but there's a lot of fat, right? There's like 18% fat. For non-fat ice cream, we have to put in a lot more. We have to put in about 1% because there's no fat. So it kind of changes the consistency and the structure of the ice cream. So if we add up all the solids, so if we take all these things, the fat, the milk solids, not fat, the whey solids, the sucrose, the corn syrup, the stabilizers and emulsifiers, we come up with the total solids. Whatever's left is water. Okay, so for instance, in non-fat, we have about 35% of total solids and about 65% water. For super premium, we have about 40% and about 60% water. So notice that we had to play with things to get about 35 to 40% total solids. But they're all around that range, no matter if it's non-fat or regular or super premium. And there's about the same amount of water in all. I mean, we go between 60 and 65%. So another way of looking at this is we'll look at the fat, protein, carbohydrates, and minerals and what the percentage is. If we look at non-fat, there's 0.5% of fat, and there's about 4.73% protein, and carbohydrates about 27%. So don't forget, this is the sugar, whether it's corn syrup, table sugar, or or the lactose, and then we have some mineral ash. Okay, and if we look at the percent solids for basis, and if we look at super premium, about 18% fat, about 3% protein, about 20% carbohydrates or sugars, and about 0.85 mineral ash. And if we look at the percent solids basis, right, this is about 1.43 for non-fat and about 39.8 for super premium. So what is ice cream mostly? So this is a vanilla ice cream. Okay, although it's pink for some reason, sorry about that. Okay, so what we have in the ice cream are ice crystals, air vacuoles, so air cells, and fat globules. So the ice crystals are shown as blue chunks, and the air cells are shown as white. And then the fat globules, which are much smaller than the ice crystals, right? And um, and then the liquid syrup. So this is the water, the sucrose, and the vanillin, which is vanilla. And these are about the size of things, right? So notice that the ice crystals are much bigger than the fat globules, and right, the sugar and water, the liquid syrup, is much smaller than the fat globules. The amount of water that's actually frozen, that's actually leaves the liquid syrup and becomes ice, depends on the temperature of the ice cream. So if we look at the composition of frozen dessert, so this is something with 100% overrun. So we took a gallon of mix, we got 2 gallons of ice cream. We whipped in 50% air. So about 50% of up to 50% of ice cream, which is the maximum allowable by the FDA, is air. Okay. This decreases as you go up the scale from regular ice cream to premium ice cream to super premium. There's about 5% fat, about 15% sugar solution, and about 30% is ice. So a little bit closer look, we see there's fat and a little bit of protein, a tiny bit of minerals. There's sugar and corn sweeteners. There's a very tiny bit of stabilizers and a lot of water. So this is the composition of actually the ice cream mix, right? And there's also a tiny bit of milk salts and also lactose. So this is the composition of ice cream, and this is the composition of the ice cream mix. So everything's there but the air. Okay, so first there's water. There can be 55 to 80% water. And this is a continuous phase for emulsion. So the fluid phase of a colloid within which solids or fluid particles are distributed. So it's a fluid, a liquid with little particles inside. That's the emulsion. So the colloid is a homogeneous non-crystal substances consisting of large molecules or ultra microscopic particles. So that means they're bigger than microscopic, right? You can see them without a microscope, of one substance dispersed into another substance. And colloids include gels, solutions, and emulsions. And the particles in emulsion do not settle and cannot be separated out by ordinary filtering or centrifusions like that of a suspension. So with this water, part of it is frozen in the manufacturing process, and it's the melting of the ice that provides the refreshment that you feel from ice cream and other frozen desserts. The ice crystals determine the texture, so determine whether it's smooth or coarse. So the bigger the ice crystals, the more coarse it is. And the state of the water is temperature dependent. So the more I freeze the ice cream, the more water is frozen. Okay, this is different than what we read when we talked about water in the last lecture where we discussed heat and temperature. We said what happens is we bring the water down to 32 degrees Fahrenheit or 0 degrees Celsius. And if we keep cooling it off, the water and ice, so ice will begin to form, and the water and ice will remain at 0 degrees until all the ice freezes. This isn't true of water that's held in ice cream. What happens with the ice cream is the colder you make it, the more water freezes. And we'll talk about that in a couple of chapters. But for now, realize that the state of the water, how much of it turns into ice, depends on how cold it is. We need to make a couple of definitions here. So first is something called equilibrium. So physicists consider something an equilibrium when all the forces add up to be zero. So for example, someone's pulling you to the left and somebody's pulling you to the right with an equal force, then nothing happens, right? You just stay there. So the equilibrium, and we think of the net force, the total of all the forces being zero. So in ice cream and in food science and chemistry, right, equilibrium is a condition in which all the influences acting cancel each other out so that a static or a balanced situation results. So in physics, equilibrium results from the cancellation of forces acting on an object. So there may be a whole bunch of forces acting, but they're acting in such a way as to not affect you. It's also rheology, which is a branch of physics that deals with the deformation and flow of matter, especially non-Newtonian flows of liquids or plastic flows of solids. We also want to define something called mouthfeel. So this is the product's physical and chemical interaction with the mouth. And it's an aspect of food rheology. And it is used in many areas related to the testing and evaluating of foodstuffs, such as wine tasting, right? So, for instance, if you've ever been to a wine tasting, you want to know how the wine feels in your mouth. So this is the mouth feel. There's also bulking agents. So these are additives such as starch that increase the bulk of the food without affecting the food coloring. Sorry, there was a note there from a previous class that says finished here, but we're going to keep going. So sugar. So sugar is about 13 to 36%, depending on what kind of ice cream you buy, right? And sugar is a sweet crystalline substance obtained from various plants, especially from sugar cane and sugar beets. And it consists essentially of sucrose, and it's used as a sweetener in food and drinks, right? And in biochemistry, it's any class of soluble crystalline, typically sweet tasting carbohydrates found in living tissues and exemplified by glucose and sucrose. In this case, it's the primary solute. So solute is the minor component in a solution dissolved in the solvent. So in this case, the solvent is water and the solute is sugar. So we have a syrup that's a fluid, and it consists of water, the solvent, and sugar, the solute. And it helps set up the water ice equilibrium. So depending on how much sugar is in there, it's going to depend on how much water freezes at a given temperature. It's a sweet taste. It also provides mouthfeel, and it's also a bulking agent. So what we see is that the percent of frozen water actually increases as the temperature decreases. So if we start at, say, negative 2.5 degrees C, there's no water frozen. When we get to negative 10, we have about 65% of the water is frozen. And if we go down to negative 30, we end up at about 95%. Realize that at this point, there's most of the water is frozen at negative 30 degrees C, which means that it's going to be incredibly hard, right? It's almost going to be crunchy at this point. Also in the ice cream, we have 0 to 22% milk fat. So this is emulsified, and what we find is that the protein covers these particles of fat. So if we look at the fat globules, there'll be protein covering them. And the way these melts or crystallize gives you some more mouthfeel for your ice cream. too much milk fat, and it can become actuous, which means um, having the quality or characteristic of oil. So it tastes like you're eating oily, something oily. So it's containing or composing of oil or fat, whereas an abundance in organic materials, and it's soft and rich. It can also make it creamy. So you want enough milk fat that your ice cream is creamy, and you don't want so much that it tastes like you're eating oil. It's also a cold depressant, and it adds some flavor, right? And it could be good or bad. So too much milk fat will actually start to make it taste bad, right? But just the right amount makes it taste good. There's also proteins, right? And if we look at proteins, these are and they're 0 to 5%, and a lot of these protein and the protein comes from the milk, and it helps with the surface activity. It also helps to emulsify the fat, so the fat doesn't separate. Doesn't separate. So um, before things were homogenized, before milk was homogenized, you would get milk and the fat would float to the top and the rest of the milk would sink to the bottom. So this protein will actually help emulsify it. It also emulsifies the air, so it helps with the overrun. It adds texture and body, and also it adds some flavor. But don't forget, there's only 0 to 5%. But if there is too much protein, then it could start to taste, it wouldn't taste as good. There's also stabilizers. So these are hydrochlorides and that are water soluble. So they disperse in water. And they're commonly used in ice cream. So here we see xanthine gum and gar gum are two things that are used. And stabilizers are extensively used in the ice cream industry. Uh, they include gar gum, locust bean gum, carboxyl, ethyl cellulose or CMC, and some more, right? And gelatin and carrageenan. And these stabilizers are derived from plants, bacteria, and animal byproducts. So the stabilizers are a water control agent and they increase the viscosity of the ice cream. And viscosity is a measure of how things flow. So when I think of viscosity, I think of viscosity as the friction between layers of fluid. So this is how we measure viscosity. What you do is you take a funnel and you fill it full of whatever it is you want to test, and you time how long it takes to leave the funnel. So for instance, water has a very low viscosity. If I filled the funnel, it would quickly disappear, like drop through the funnel. Pancake syrup or maple syrup has a much higher viscosity. If I filled the funnel full of maple syrup, it would take a while for it to spill out. So the stabilizers increase the viscosity of the ice cream. They also add to the mouth feel, right? And they delay ice crystal growth. So I mentioned a couple of times that if you leave ice cream in the refrigerator in the freezer for a really long time, what will happen is the ice crystals will they'll melt and freeze again and melt and freeze again, and the ice crystals get larger and larger. In fact, sometimes you'll actually start to see them, right? In which case, the mouthfeel isn't as good. So stabilizers delay this ice crystal growth so they don't become too big. There's also emulsifiers. So here shows what happens when we have emulsifiers and when we don't have emulsifiers. So we took a chunk of ice cream and we took it out of the freezer and put it on the table. So the top one is without emulsifiers and the bottom one is with emulsifiers. And what you see is that after a while, the ice cream melts into a pile of stuff, right? in essence, it returns to its initial mix, kind of. But with the stabilizers, it maintains its shape for a longer time. So emulsifiers add some firmness and some dryness, right? And they stabilize the overrun so that air doesn't leave the ice cream and it shrinks. Sometimes you'll see that if ice cream's there for a really long time. Okay. It also enhances the texture. It keeps the shape better and controls the meltdown. So I don't know if you've like ever had too much ice cream in a bowl and you didn't eat it all, especially you're out at a restaurant or something, and suddenly it's like sitting on the table and now there's a pool of melted ice cream, right? So, which might not be very appealing. So it controls this meltdown. And since it stabilizes the overrun and doesn't let the air leave, then it reduces the shrinkage of the ice cream. Emulsifiers are interesting because what they have is a hydrophilic part and a hydrophobic part. Hydrophilic means water loving. So it means it has a strong affinity to water and it tends to dissolve in or mix with or be wetted by water. Hydrophobic means water fearing. So it's repelled by water and it tends not to try to combine and it's incapable of dissolving in water. So these emulsifiers have um, a hydrophilic head and a hydrophobic tail. So what happens is it finds a chunk of fat or protein and it sticks its tail into the protein and the head points out uh, from the material. So in this case, you have this water loving part that sticks out and and combines with the water, and then you have this water fearing part that sticks into the fat or protein. And here just shows a better picture of the same thing, right? What happens is um, the hydrophobic tail goes into the milk fat, and the hydrophobic and hydrophilic head sticks out the other side. There's also some trace components, so um, that are in parts per million. Okay, and for instance, they help with the sensory, so the taste and feel, appearance and feel. So, for instance, we put vanilla in, right? There's not much vanilla compared to the other things, right? We add a little bit of salt. There's some organics in there. There's also some things that help um, it not freeze, so that the whole thing doesn't freeze to all the water doesn't freeze. And there's some trace components to help with viscosity and protein stability. By the way, the pH is a measure of hydrogen ion concentration, and it's a measure of acidity or alkalinity in a solution. So an aqueous solution at 25 degrees C with a PS of less than 7 are acidic, and aqueous solutions at 25 degrees C with a pH greater than 7 are basic or alkalinic. And a buffer is a solution that resists changes in pH when an acid or an alkali is added to it. So buffers typically involve a weak acid or acrylic together with one or more salts. So when we think of things that are acidic, maybe think of things like adding fruit to your ice cream. There's also a couple of special purpose things that you'll find in ice cream, maybe some starch, um, some polydextrose, alcohols and enzymes, and sugars and fat substitutes. Also, what we have is um, some flavors and colors can be added, right? So these are mainly for sensory, so for taste and appearance and texture. Okay, and they're soluble particulates, so they dissolve, right? And the variegants can be mixed in, so that's anything that you mix in, such as nuts or fruit or candy pieces. They might be natural or artificial. Okay, so for instance, we'll talk in depth about vanilla and how vanilla is actually pretty easily made artificially. Okay, and there's an infinite variety of these, right? Okay, and some of these can start to deteriorate, right? You might have to worry about them after some time deteriorating a little bit and producing some bad flavors. So variegates add the unique texture and taste to your frozen dessert creation and make it stand out in the minds of those who taste it, right? So variegates are anything that you add in or mix in. A really important part of ice cream is air. So this is in the form of foam or frozen form, and it imparts the structure to the ice cream. So the size of the air bubbles actually determine the textural stability. It also helps for the flavor release. So flavor are volatiles in a gas phase. So so when things are really cold, you don't taste them very well, right? But as they melt in your mouth, you can taste them. And also, of course, air is good for profitability, right? Let's face it, if you can take a gallon of mix and make 2 gallons of ice cream, it's probably a good thing. So the size and number of particles in ice cream, if we look at, for instance, fat globules, there's the average is about zero point 0.5 nanometers. So a nanometer is 10 to the minus 9 meters. And the air molecules, they're much bigger, right? So they're almost 100 times bigger, right? Or I'm sorry, the air cells, and they average about 60 nanometers. And the ice crystals can range from 25 to 48. So they should be about half the size of the air cells. So the smallest things are the fat globules, and then the ice crystals, and then the air cells. And the number in a gram of ice cream, right? So there should be a whole bunch of fat globules, right? So there's almost 10 to the sixth times more fat globules, but they're very tiny as compared to air cells and ice crystals. Here's an actual um, photomicrograph, right? This is a picture of ice cream magnified a bunch of times, right? And what you see is that there's ice crystals are shown, and air bubbles are shown, and the sugar solution. So here's a little bit easier picture to think about, right? What we have is water and sugar. So that's all this kind of pinkish area. Then there's air bubbles. They're these white circles. Then there's ice crystals, and they're smaller than the air bubbles. And then there are fat globules. They're smaller than um, the ice crystals. And then milk proteins are smaller than the fat globules, and they actually add combine with and help emulsify. So if you notice, they like to stick to the ice crystals, the air molecules, and to the fat globules. So as a summary, right, we have ice cream as a mixture of air, water, milk fat, or non-dairy fats, milk solids, not fat, sweeteners, stabilizers, emulsifiers, and flavors. And the ice cream mix is the unfrozen blend of ingredients used to supply these constituents. except for the air and flavoring material. So that's the ice cream mix. Mix formulation, that's a percentage of the constituents. So the fat, the milk solids not fat, the sugar, the stabilizers, and the emulsifiers. And there's a wide variety of ingredients, right? So milk fat and milk solids not fat can come from cream, butter, fresh, condensed or concentrated or powdered whole or skim milk. So here we have a table from your book, and it shows you the constituents and the functions and the limitations. So the milk fat is used to increase richness of flavor, and it lubricates and insulates the mouth, right? They're expensive. They also hinder whipping, and they might limit consumption due to the high calories and satiating effect. So if you ever noticed, if you have really, really rich, expensive ice cream, you might not be able to eat a huge bowl of it because it's just too rich. Okay. We also have non-dairy fats. So they provide a good structure at lower cost, but they contribute little to the flavor, and they may actually even give you a bad flavor. So these are other fats that you can use and replace some of the milk fats because the milk fats are expensive. And they may contribute to a greasy texture. We have milk solids not fat or milk whey protein concentrates, right? These are all the same thing. And don't forget, the milk solids not fat is when you take milk, you remove the fat, you take away all the water, what's ever left. So the milk solids not fat are going to be a little bit of protein, a little bit of sugar called lactose, and mineral ash. They improve the texture and the and body of the ice cream. But in high amounts, they can actually give it a cooked or a salty flavor, right? And they have the potential for sandiness. So this lactose crystallization. So the lactose actually starts to form crystalline sugar. The whey solids are less expensive than conventional milk solids not fat, right? But they have a high amount of lactose, will cause freezing point depression. So it's harder to freeze it. And there's a potential for sandiness or graininess. Sugar, of course, it's great because it imparts sweetness to the ice cream and improves flavor and texture. It also lowers the freezing point. Corn syrups, they're lower cost than sugar. They improve body and texture, increase the stability of the ice cream. Some people think that they impart an off flavor and a chewy texture, especially if you use too much. It's also stabilizers. They enhance smooth texture and provide body and enhance shelf life. But if you have too much, then they can actually make the milk feel chewy, and it increases melt resistance. And don't forget, part of the enjoyment of the ice cream is that when you put it into your mouth, it melts and then gives off some more flavor and also has a cooling effect. But if you add too many stabilizers, that actually you won't get that effect. Also, egg yolk solid. So this improves whipping ability, but it imparts a custard flavor. However, too much of it, or if it's put in the wrong way, and we'll talk about that in the next lab, then the egg flavor, it might actually taste eggy. And for somebody like me that doesn't like the taste of eggs, it probably isn't a good thing. It also leaves for a foamy melted product. So as it melts, it starts to get like a little bit foamy from there. There's emulsifiers, right, which promote fat destabilization, and they lead to dryness and smoothness and good melting properties. Okay, and if we look for total solids, this provides for a smoother texture and a firmer body and a higher nutrient concentration. If we look for flavoring, it increases acceptability, right? So adding vanilla to our ice cream makes it taste much better than if there was no vanilla, right? And the coloring, you have to be careful because some people are allergic to certain colors, and it can actually give you like a fake shade. So, for instance, some people hate um, when pistachio ice cream is green because there's artificial, because it's clearly artificial coloring, and some people can actually taste that coloring. This shows the minimum standards for various countries, right? So in Australia, the minimum milk fat is 10%, and in the United States, it's 10%, right? Um, and if we look for Finland, it's like 8%, right? And the United States is the only one that has um, a requirement for total milk solids, right? And the weight per liters, once again, this shows how much overrun there is. So if we look at the average values for fats and total solid contents and overrun and the cost, right? So for if we look at economy ice cream, legally the fat is 8 to 10%, and the legal minimum is usually about 35 to 36%, and the overrun is the maximum overrun, and its cost is low. So for standard ice cream, you could have overrun from 100 to 120%. For premium, the overrun's about 60 to 90%, and super premium only has a quarter to half a percent, right? 25 to 50%. The more expensive the ice cream, the higher the percentage of total solids and the highest percentage of fat. Okay, so as the fat content increases, the milk solid non-fat must decrease, or else the ice cream becomes too viscous, and there's a potential for sandiness, which results from the crystallization of the milk sugars. The milk sugars, which are lactose in the finished product. All right, so let's look at these different types of frozen desserts. There's ice cream, custard, reduced fat, light, low fat, non fat, bulky flavored ice cream, gelato, Turkish ice cream, soft serve ice cream, and Melorine. So frozen custard. It's roughly the same as ice cream, except egg yolks are added. So in the US, the minimum egg yolk solids are 1.4 or 1.12%. It's also known as French style ice cream, okay, or Glance auf, which is 7% egg yolk solids. And also there's the German, which has 240 grams whole or whipped eggs per liter of milk. There's reduced fat ice cream. Reduced fat ice cream means that it's 25% less than the reference ice cream. So if, for instance, Breyers has a vanilla ice cream and they come out with a reduced fat version, then the reduced fat has to be 25% less fat than their regular vanilla ice cream. So light means that there's usually 50% or a third the calories than the referenced ice cream, where the reference ice cream would be what they consider their base ice cream. Then low fat, not more than 3 grams of milk fat per 4-ounce serving, right? And it can weigh as little as 60 grams. And non fat has to have less than zero point 0.5 grams of milk fat per serving. And it can contain no ingredients that add fat unless asterisks add trivial amounts of fat. Bulky flavored ice cream, this just means a significant volume of coloring, flavoring ingredients such as cocoa, fruit, nut, confections, or sugar. So the U.S. reduction in the minimum fat, so there's 2.5 times the weight of cocoa or 1.5 times the weight of fruit juices, right? So the weights of dehydrated fruits or, or fruit concentrated may be calculated at their natural state by before multiplying it by the 1.4, right? So this is bulky flavored ice cream. How about gelato? That's Italian style ice cream, and it's typically lower fat, so it's 4 to 8%. It has a lower overrun, so less air whipped into it, but it has a higher sugar, so up to 25%, including cornstarch such as high fructose um, or high maltose syrup. And it's more soft and pliable. And its traditionally serving style is fresh, soft frozen or scooped, and they have these really well decorated shallow stainless steel serving trays. So it's highly intense in its fresh flavor. There's Turkish ice cream or Maras ice cream, and this is much more elastic texture. So it contains salep flour, and which is flour from the orchid root, and it contains mastic, which is a resin that imparts chewiness. So the Maras style is so sticky that you actually need a knife and fork to eat it. We also have soft serve ice cream. So this is the not hardened. It's served directly from a surface scraped freezer. And finally, we have Meloran, and that's where you replace some of the really expensive but good tasting milk fat is replaced entirely or partially by vegetable fat. Okay, so this is our introduction. This was our introduction to the ingredients that are used in ice cream, and also we gave some definitions of the different types of frozen desserts. Okay, and thanks for your time.